With proof by induction, what you normally have to do is read what you're trying to prove, and then you just assume the complete opposite. And when you assume the opposite, something will go wrong with your proof. There will be a contradiction, and that means that the original statement must itself be true. So in this example, we've got to prove by contradiction that if n squared is even, then n must be even, which makes sense, really. I mean, if you think about 16, for example, 16 is even, and the square root of that 4 is also even. Same with 100, 100 is even, and the square root is also even. So it looks like it's going to be true, but of course that isn't a proof. It's just two examples where this works. So in order to prove it, we're going to use proof by contradiction. So if we assume the opposite of what's written here, if we assume that n squared is even, but n is odd, then if n is odd, then you can write n as 2k plus 1, where k is an integer, and so n squared will be 2k plus 1 squared, which is 4k squared plus 4k plus 1 if you expand the double brackets, and that can be written as 2k plus 2k squared plus 2k plus 1. So this is obviously even, and so when you add 1, this must be odd. So what we've just shown there is that if n is odd, n squared is odd as well. But that is a contradiction. So it's a contradiction, so we can write a symbol there which means contradiction. It's a contradiction because we found that n squared is odd, whereas we assumed that n squared is even. So it's a contradiction, which means that therefore the original statement must be true. So therefore, if n squared is even, n must also be even. So that is our proof finished for that one. Here we have a very similar question. So what you might want to do is try this one yourself before I go through the solution. So you might want to pause it now and see if you can do this. So it's very similar to the last question. If we assume that n squared is a multiple of 3, but n is not a multiple of 3. So we're assuming the opposite, so something should go wrong, but we'll see what it is in a minute. So if n is not a multiple of 3, therefore n could be either n could be 3. So if n was a multiple of 3, it would be it would be 3 times an integer, so n would be 3k. So if n is not a multiple of 3, it could be 3k plus 1, or n could be 3k plus 2. So neither of these two numbers, whatever k is, it doesn't matter because k is an integer, so both of these numbers would not be multiples of 3. So if we take this one first of all, then n squared would equal 3k plus 1 squared. And if you expand that, you'll get 9k squared plus 6k plus 1. And so you'll get 3 times by 3k squared plus 2k plus 1. If we were to do the same for this one, then n squared would equal 3k plus 2 squared. So n would be 9k squared plus 12k plus 4. And then we can take out 3 from here. Like this. Actually, we could let's just take out, let's put 1 here, and then that'll be a plus 1 as well. You could see that times that gives that times that gives that, and that times that gives 3, which means we must have a 1 left over. So that means that this here is a multiple of 3 here. So that means all of this, the whole thing, is not a multiple of 3. And similarly over here, this is not a multiple of 3. But that is a contradiction. So let's get our big contradiction sign. It's a contradiction because we assumed that n squared is a multiple of 3 up here. Okay, so because we got that contradiction, we can say therefore if n squared is a multiple of 3, then n is also a multiple of 3. So we have proved the original statement is true now.